Okay, now it seems that the number has been stabilized. Very welcome everyone to this webinar on ESD simulations. This is the second webinar on this topic that my dear colleague Vesna Somero will present shortly. I will leave the stage to her very fast so we can deep dive into technical part. But before that, just some technicalities about the webinar. For those of you who don't know me, my name is Moaz Karzadeh and I will be your host today. Uh, practicalities of the webinar, as you can see, it's already been recorded. So you will have an email by the end of the week that you will get the recording. Feel free to forward it to the colleagues who couldn't make it today to look at it. And also, if you want to look at it, having another look, you will have it in your access. For questions, you can use the chat to ask the questions. You can write to me to ask the questions. And the end of the session, we will try to answer them if we hopefully have time. But also there is this new app in Teams called Poly. Up there, you can see it. You can write your question there. And in the end, also, we will have now it's actually popping up so you can see the box. In the end, we will go through your questions. And also the chat, please feel free to write comments, thoughts, questions, use it as a dynamic, basically like a conversation place, but please make sure that your cameras and microphones are off. A couple of slides just about PLM Group. Most of you know PLM Group, but for those who don't know, we are platinum partner to Dassault Systems, serving all 8 countries in Nordics and Baltics, more than 200 people and around 20 offices that we go from. And this is my last slide. This is basically an overview of different solutions that we do. We have a big department inside CAD solutions, such as SolidWorks and CATIA, inside PLM and PDM, such as the 3D Experience Platform and SolidWorks PDM. Inside simulation, of course, we do electromagnetic simulation, ESD, EMC, but also we do other simulations, such as a structural, a CFD, and motion, for example. We have the biggest reseller in 3D printing in the Nordics also. It's our sort of like sister company called Adinor. And then we also have solutions inside automation and CAM. This was just overview of PLM Group. I'm not gonna get more of Vesna's time about this. So without further ado, Vesna, please take over and carry us away with your amazing simulations.
Thank you so much, Mo. And hello, everyone. And thank you for tuning in. For those of you who don't know me, I'm Vesna. And as Mo already explained, I will be presenting today on the topic of air ESD. I will talk a bit about fundamentals of the phenomenon and one way how we can perform simulations. So let's get started. I will start sharing my screen and please, I will steal from Moe. So if hopefully you can now see my first slide, pardon?
Yes, we can do.
Okay, great. So first, why? Well, air ESD is a very interesting phenomenon, at least to me, and quite a mysterious one when it comes to electronics development. How we can define it, it's an electrostatic discharge event that happens through the air and not through the direct contact. And it occurs via ionized channel that gets established like a conductive path between charged objects. So sounds like a quite a mouthful and complex, but actually we have quite a good examples in nature, as you maybe already know. And one fact is that electrostatic discharge through air is under a great influence of the environment and the environmental conditions, for example, the weather. And this summer, maybe you have witnessed some summer storms, and the high humidity and other atmospheric conditions increase the likelihood of spontaneous discharges. And basically, the lightning is the most dramatic example of ESD, where we have millions of volts discharging from the clouds through the ground through air. Of course, while lightning strike is quite dangerous, and actually it can be also simulated using CST Studio. Today I will not be talking about that topic. Today, I will more dedicate this time on this kind of smaller zaps. And if you, especially you're familiar with the northern climate, during winter, the air can be very dry. And that presents ideal conditions for buildup of static charge. And in those cases, even a very nearby approach without needing for a direct contact can trigger electrostatic discharge through the air. And while those small zaps are not dangerous for people, unlike lightning strikes, they are devastating for sensitive electronic devices, which is why air ESD understanding of it is essential for product development and of course how to tackle the issues caused by the air ESD. So this is the overview of today's topics. And the star of today, of course, is CST Studio Suite. And I also would like to use the opportunity to recommend an excellent paper, free white paper, which can be found on Google, and maybe Mila can also share the links, called Electrostatic Discharge by Dassault. And it gives a great overview on the phenomenon and how the ESD gun, how this whole ESD setup is modeled using CST Studio. I will present that in the following during this webinar. But I will overview first the physical phenomenon, then it is important to understand the difference between air and contact discharge. A little bit, I will talk about the differences in standards and testing, so there will be some tables. And of course, what I would like to really pay attention is the product quality, not only compliance. I will overview very briefly mitigation techniques for tackling ESD, and then I will finish with a hands-on session. And while this agenda gives very structured approach to ESD air discharge simulation, my aim here is to inspire for proactive and creative problem solving. So not only to present a workflow, but more like drawing from the real world product development, encourage you to have a fresh perspective beyond standard methodologies used for ESD tackling. And my approach to knowledge is and knowledge sharing is more to teach you how to fish rather to just give you the fish, if you understand my analogy. But let's start fishing now. And in the last session, in the last webinar, I have focused on the basics of contact ESD and how it is generated. Just to quickly recapitulate, is that due to the triboelectric charging via friction or even walking on a synthetic carpet can create charge separation and buildup of static charge, so that contact discharge happens through the air when via that contact we have released discharge current. And contact ESD by nature is generally more repeatable. It's better controlled and easier to even measure in the laboratory environments. In contrast, air discharge is less predictable and it is harder to test consistently, which is why sometimes it is difficult to recognize the failures coming from air discharge in the earlier phases of product development. And of course, this unpredictability makes air discharge especially critical for system level design and robustness, which is why it requires proactive and not reactive dealing with it. And one way, the best way in my opinion, is using simulation. And again, briefly on the physics behind the air discharge. As already mentioned, that electrostatic air discharge can jump across an air gap without any physical contact. And it is, while in the basics, it's similar to contact discharge. So we have the accumulation of charge and potential difference, which then means that we will have electric field established between charged objects. Now, when that field strength exceeds the breakdown voltage of air, which is a medium, perhaps you're familiar with solid-state electronics. So when that breakdown occurs, it will start so-called avalanche ionization. Breakdown voltage of air under normal condition is 3 kilovolts per millimeter. And the avalanche ionization basically means that there are few free electrons in the air that exist, and they get accelerated by the influence of the electric field that now exists due to this potential difference. They will then hit other neutral particles like ions or molecules in the air and bump out of them more free electrons. So this all starts one chain reaction, which then will establish this kind of so-called avalanche ionization. And we will have basically current across the air, or we call a spark. And it is, I mean, of course, it is logical that to understand that now the key factors is the environment and the medium where this breakdown occurs, which is why some key factors that affect it are humidity, of course, the distance, and the field strength, which reflects how much charge has accumulated on those objects. So in winter, for example, when charge separation is easier, we will have higher level of electric field across the gap. And so this is just briefly overview of how humidity affects testing of air ESD. And as I mentioned, that the nominal or normal value of humidity is between 40 and 60%, and then the breakdown voltage of air is considered to be 3 kilovolts per millimeter. However, if the air is dry under winter conditions, the breakdown voltage increases, which means that electric field strength needs to be a bit higher than this nominal value for the spark to occur. But on the other hand, during the dry conditions, the charge builds more easily. On the other hand, under the humid conditions, due to the more moist in the air, we will have more free carriers, which is why breakdown voltage slightly decreases, which is then it means that it's easier to ionize it and to start the avalanche. And also one note is that air in general is easier to ionize than the dielectric. If you remember, the dielectric will form those dipoles, then it will form inner electric field that will oppose this external electric field coming from the charge, which is why the electric is more difficult to ionize and requires higher breakdown voltage. So now when we know some basics in the physics, I have just highlighted for these key differences. So key difference is, of course, the mechanics, that mechanism that is causing it, not a direct contact, but avalanche ionization in this case, across the gap without physical contact. So normally that the use case in the tests will also be when the conductive surfaces are actually not accessible as well. So in addition to also accessible conductive surfaces or contacts. And the trigger condition is the breakdown voltage, which makes air discharge highly sensitive to the environment. Of course, that also could mean less predictive and more variable, which is why it's quite challenging to measure it. So when we talk about testing, I will talk about this standard IEC 61042, and this standard covers both air and contact discharge. And in general, products need to pass both of those discharge testing of a certain level. And these are the main differences between in the terms of testing. Obviously, that because of the definition of air discharge, also the application scenario will be different. But we also have slightly different equipment. So for contact discharge is used sharp metallic tip that is applied directly on the conductive surfaces, while in case of air discharge, we have a rounded tip, then is also applied to the outer housing and gaps and coated surfaces. Naturally, protection strategy will also differ, because we have actual physical conductive path. In the case of contact discharge, we can use grounding or low impedance paths, as well as the TVS diodes and other ESD protection components. But in case of air discharge, in addition to that, we need to take care of the environment. So we need to apply different methods like insulations and shielding and gap control. And again, a little bit more about the test, which is relevant. So the standard that I was talking about for system level testing I've listed here 4 levels. And in the right upper corner, I have also placed the current discharge waveform estimated for contact discharge. So now if we compare the voltage applied that is deployed by the equipment or ESD gun, we can see that for level 1 and 2, the applied voltage is the same strength, while for level 3 already we have a higher air discharge voltage being deployed, and for level 4 almost twice as the value of contact discharge. Now, peak current, I have to say these are more estimation currents. For the contact discharge is given in this table 3, and then in table 4, I managed to find also estimated peak current for air discharge. So we can notice that not only the estimated peak current for the same level is almost twice as high in case of air compared to contact discharge, but also the variation of this estimation is quite wide, almost the third of the value of the maximum value of the estimated peak current, which only basically speaks on the unpredictability of air discharge and how it can present quite a big challenge for product development. And now, of course, I talked about testing, because in compliance, we follow certain standardized setup, and the device under test either passes or fails the test, whether it withstands or not a certain level of testing without any malfunction. And this is quite straightforward test. but doesn't provide any information on the discharge behavior or behavior the product under the ESD stress. So on the other hand, measurement would focus on capturing actual voltage and current waveforms, and this would allow for deeper analysis, such as rise time and energy. And it's typically used in contact discharge by using a transmission line pulse analysis as a preferred method, and common for characterizing, like, for example, ESD protection devices. However, in case of air discharge, this high variability due to different factors makes the waveform or measurement very difficult, which is why testing is preferred method for air discharge and not measurement. Now, of course, just to kind of highlight beyond the compliance, compliance requirements, of course, aim to ensure that device can withstand real-world ESD events. But in some cases, testing is really not enough to ensure the quality of the product in long term. So our goal is not to only pass the test, but to have reliable devices that last in the field. So we really need to understand what are the main challenges design-wise. And those are quite often overlooked features. So a little less obvious features like seams, gaps, coatings, and floating parts that often go unnoticed but can accumulate high concentration of electric field and trigger ESD events. So, okay, why simulate? Because, well, apart from the, except from the fact that it's fun, simulation also helps visualize ESD behavior and product behavior and find hotspots and other vulnerabilities of the product design. And with this insight, we can improve the design before the final stages of product development and, of course, before the testing, saving time and certainly the cost of product development. In this slide, I've just briefly overviewed mitigation strategies. This is not topic on the design strategies. I think that there is a specialist in each of these areas. But one important highlight is that simulation-guided design is a key for applying these different mitigation strategies in the most effective and timely manner. So they can be PCB design strategies that refer to maybe the layout and routing practices, then mechanical design considerations from gap reduction to placing different enclosures. And finally, we can also resort to the system level fixes, like power management strategies or firmware debouncing. However, system level fixes usually combat failures coming from Air ESD too late in the product development, which is why it is much better to left shift with the simulation guided approach. So if I've convinced you that simulations are absolutely necessary, for air discharge, I would like to present one three-step approach for simulating air discharge. And step one, basically, as I talked about, the nature of air ESD is that it's very unpredictable. So the step one would be to try to predict where the spark location will occur. So the spark is basically determined by the electric field strength And we can use a couple of different methods like common sense, experience, and we can use simulation to kind of try to predict the occurrence of spark. If we're just looking with a bare eye, we can maybe notice some arc-prone areas like gaps, sharp edges, exposed metals. But it would be actually much better to use a static field solver to visualize the electric buildup, and based on that, estimate the probability of the spark occurrence. Now, let's assume that we know how to use it and we have somehow estimated where the spark will jump. Then we can go to step 2, where we can quantify the impact that this arc or spark has on the DUT. We can then conduct call simulations where we can observe currents, voltages, but also electric field distribution, and analyze different scenarios to understand how the spark affects the layout and current flow throughout this device. And of course, see what are our vulnerable parts of the design that we could improve. So once we have also done that, we can then continue finally to the mitigation. So using the knowledge from steps 1 and 2, we can apply smart design strategy from mechanical, so refining the geometry, or adding groundings, return paths, and so forth to tackle the risk of the ESD damaging our product. So what I will show next will, of course, be the step 1. So how to predict the spark before it actually happens. And before that, I will just overview the DUT that I'm using in this webinar. So it's the same as the one from the previous where I used for contact discharge. So this kind of device is inspired by the small wearable devices we are surrounded nowadays, and presents 2 sets of challenges. One is that it has metal pins, floating parts, and that are a common location for ESD event to occur. And then we have a small form factor without any external path for the discharge, which means that a lot of energy stays in the system before it manages to dissipate. So we have the back plastic cover and some exposed metal parts, and the front we have a display. And then after what we have under the hood, so under this plastic back cover, I have this kind of metal backplate, which I will play with it being floating or grounded to see the effect. And I assume that these pins would be charging and data exchange contacts. Then we have this kind of battery with 2 terminals, like a ground and a voltage terminal, and very simplified display that I also explained in the last webinar. It's kind of LCD type of display. And then a very simple PVB, and in static solver, I will just have a full solid PVB without any layout. So this would correspond to the starting phases of the project, where we still need to gather the insights to evolve the design. So just before I jump into the static solver, to say that it is a low frequency solver used for static electric problems. And in this case, I use it like for spark prediction. The main task for static solver is to calculate electric field strength and electric flux density. So we can observe the electrical field distribution and use so-called streamline tracing to analyze and identify electrostatic discharge behavior and spark formation. And if you haven't used streamline plots, so streamline plots are paths that follow the direction of the electric field. And in static solver, we can choose so-called field-based seeding, which means that we can select the points with the high electric field strength, which helps us visualize and assess those sensitive areas that can cause the charge or the spark to occur. And more on the static solver you can find, of course, in CST help, and there are quite a few also examples. And before I walk you through the simplified model, the first step in static solver is to define, of course, to have the model, and from the model to define the sources. Static solver has various options for sources, and in this case, I've chosen to use potentials as source type. Therefore, here I have as a source potential, I have the fingertip. Of course, in a real scenario, this could represent something like the tip of an ESD gun, and it's only for kind of illustrative purposes. And to assign potential source in electrostatic solver, the material needs to be assigned as PEC. So all these potentials here have to first have PEC, need to be PEC. And I have also assigned PCB to 0 volts because it represents a ground potential and it is connected to the battery. Now, then we have the pins, which I have here assigned. V bus is the second pin. So first pin is grounded as in the description. Second pin, I have assigned it as V bus. And normally it would be some maybe 3.8 to 5 volts. So I have assigned 3.8 volts, and those other pins are actually floating. So in real situation, they would be connected to through some impedance to the ground or to some nets, but for clarity, I've kept them quite simplified. And now speaking of comparison, so the focus is to keep my source in the exactly same location. So the finger is kept in the same location. And what I will do is vary different grounding paths, material properties, and position to explore how geometry and those factors influence electrostatic behavior. And we will observe electric field distribution and the streamlines. So as a reminder that the spark or fall is governed and determined by electric field strength, and also the spark will always follow the path of least resistance. It depends on, of course, as we will see, on geometry and also on the materials which reflect the ionization. But let's go hands-on CST, and I have already opened my model. So I hope you can see now my model as well.
Yes, we can see it.
Great. So in this first baseline, so I have this finger that I've taken from the phantom hand, and I've just selected this tip of the finger to be my source, so PEC. So here we can see the sources and the way we can select from different types of sources in this solver. So power ground, my PVB is a solid PVB to ground, and then I have these 2 pins are floating, and we have V bus, which is 3.8 volts. Now, of course, before we simulate, I want to just highlight that initially I have, for this, grounded this back metal plates indirectly, so via this block that represents a vibrator and this kind of block contact. And the battery contacts are also grounded through the PVB. So static solver is everything happens on the DC, and it disregards the dielectric dispersion properties. So it is not, the permittivity is not frequency dependent. And I have some other parts. So in the setup of the solver, we can of course use also the adaptive mesh refinement if we need. And in the specials, we can set that PECs without sources I have assigned as floating. So initially they are free of charge in my before I start the simulation, and open boundary, which also is charge free. So I've of course pre-simulated, and then I will show the electric field. So of course I use the smart scaling option, and based on the colors, we can also check field at the cursor, and we don't have to, but based on color, we can notice where the highest electric field strength or even the density flux we can observe. Another use, before I go to streamlines, another useful information would be the charge. So these are the corresponding charge values to these potentials. So we can see that our source, that is 5 kilovolt potential, has this amount of positive charge in coulombs. The PVB ground has almost the same, but not exactly, amount of negative charge. And V-bus also, which is exactly this second pin here. So this is the ground and this is the V-bus, has also certain significant amount of charge. Then we have this other floating part, like this battery field, battery shield, and this other floating has quite much lower amount of charge accumulated. So based on this, we can now put our view. So if you have ever used the streamlines before, so the streamlines are paths that follow this direction of the electric field and show where the electric, how the electric field is, where is the strongest. So we can visualize important areas and including those less obvious regions. So also in properties, we can set up how this plot style for the streamline. So it can be, they can be lines or they can be cubes. And in this case, I'm choosing this field-based feeding strategy. So this field-based seeding means that it selects the points with the high electric field strength. And another thing, we can also play with the number of these seed counts. So it will give the higher number of those streamlines. So I will now leave it to this. And from this, we can say that the most probable spark location and where is the electric field strongest is it will follow the path of least resistance. So through this back plate, it will go to the ground, and also it will go to this V-bus contact. Now for comparison, so I leave everything else exactly the same, but I have removed this grounding from this back plate to see what will be now the charge distribution. And I have done the same simulation, so we can see that now this V-bus is even more intense. So, okay, the scaling is perhaps a little bit different, but we can obviously see that the highest electric field strength will be on this V-bus contact. And if we again visualize using streamlines, we can see that here we have only one streamline going actually to this floating, in this case, plate, but the more is going to this V-bus and even to this grounding contact here. So just one little detail changes the entire kind of situation when it comes to charge distribution and therefore the electric field. Now, in this third setup, I have actually put this kind of dielectric buffer, like a small buffer material of the dielectric constant of 10. And I want to see how that will affect the electric field. And no surprise, but let's hide this. And we can see now that the strength, with quite a similar scaling, the strength of the electric field now on this pin is much lower than the previous. We can, of course, also compare the fields on the plane. So instead of, we can check and we can choose the cutting plane. So we can see that here on the, especially on the edges of this pin, we have high value of electric field. And in this case, we can notice that just by adding this material, it will decrease the electrical field. And therefore, we can see how we can maybe sometimes combat this spark occurrence, of course, where it is possible. So maybe in real products, and if you need to kind of have charging contacts, it is not fully possible to add this kind of dielectric, but just for the sake of studying the phenomena. And then finally, in this, I have removed, of course, this padding, and so it's comparable to this case. And I have increased this location of this V-bus pin by 0.4 millimeter. So this distance, the shortest distance between the source actually and this metal backplate is only 0.5 millimeters. And in this case, I have lifted this by 0.4. So quite a small difference. And we can now see that the streamlines show that just decreasing the distance between the source and this pin has increased the probability of the spark forming on this location. Now, of course, we can have as many of these. So I have just given one example of the one position of the finger, and there can be infinite possibilities for that. But we can see that if we would, for example, if we would bury deeper these contact pins into the plastic, we would actually not be able to access, and the air discharge will not be so easy to occur. That's why in modern, if we think about USB-C type, that those contact pins anymore are not even visible. They are so deep into the mechanics that they are not exposed to the external contact or even the air discharge. So as the knowledge is power, so based on this kind of simulations, we can make better decisions and evolve our product in a timely manner. So let's assume now that the most probable spark location will happen on this V-bus pin, but of course it can also happen on those other pins. And we can continue now to the step 2, actually, of this webinar. But before I continue, to conclude that the geometry from this static solver, we can see that the geometry of the elements and the grounding configuration affects the spark affinity. What does it mean? It means that the tendency to initiate and travel towards a specific location based on the electric field distribution in the overall model. And of course, depending on the path of least resistance. Now, again, assuming that we now know where the spark will occur. So it's maybe some gaps or those metal pins. Next step is to understand how it will affect the layout and the current flow. And we can do that by performing co-simulations in CST Studio. And I will then briefly explain. So similarly as in contact discharge, co-simulations combines full wave 3D simulation with a circuit simulation. And in this case, I'm using TLM solver for 3D simulation. And in case of air discharge, the excitation is implemented on the circuit side, which also includes this non-linear arc model, which is represented as SPICE model. So this way, basically, we simultaneously solve Maxwell's equations in the 3D and the arc resistance equations in the time domain to estimate these currents and fields for a given model, geometry, but also arc length and ionization constant. And I will show in the soon how to do it. So first, I will guide you. The air ESD gun can be found in component library. And using the model of the gun, we can simulate also influence of varying parameters, such as arc length and ionization constant on the waveform characteristics during the discharge event. So air ESD gun here is quite similar model in 3D as in case of contact discharge. But we have this arc model added to the voltage excitation, which the SPICE model is basically Rompe-Weitzel's model, which calculates arc resistance as a function of current, as a function of arc length or the distance between the source, and ionization constant. And I talked about avalanche ionization because that ionization determines how fast this conductive channel will occur in the medium. I will then come back to this slide. Let's quickly go to the actual sweep of that gun. So as I explained, we can go to component library, and if we here search ESD, we can find this model of the generator or the gun. And it looks quite similar to the contact discharge gun, with this difference that the tip is a little bit larger and it's also rounded. And the port, the source port, actually has variable length, which is also this arc length. Here I have parameterized this arc length. So to build a full model as in contact discharge, we can vary also the strap wire radius. In my case, I have left it default, and I'm actually using inductor to ground of 600 nanohenries. But in the schema on the circuit side, we already have some predefined tasks in this model of the ESD gun. So these tasks already have the excitations, and I'm using 8 kilovolt excitation case. And we can then from here start this CST transient cause simulation. I have also have those two variables, and in this first case I will sweep the arc length from 0.5 to 1.3, and I have already resimulated. So this is the port 1 excitation of that should cause 8 kilovolt discharge, and this is the arc. So here I have a probe on the arc, so we can see that for the shorter arc length we have faster voltage rise and also slightly higher. Now, of course, you can simulate this more like 30 nanoseconds or 100 nanoseconds. I have only simulated 10, which is relevant for this webinar. Let's see how the current looks. So for a different arc length, we can see that the shorter the arc length, again, the faster and the higher is the discharge current spike. It goes up to almost 54 amperes, which is quite higher compared to contact discharge. And if we go back to this presentation, so I have already pre-simulated also the ionization constant effect. So I have kept similarly arc length of 0.7, and I have swept the ionization parameters from 0.0005 to 0.002. And from here, we can see that increasing ionization contacts means faster breakdown, that the arc forms quickly more fast across the gap, and that we have higher peak currents. So that means that the discharge becomes conductive sooner. Now, of course, this webinar wouldn't be interesting if I wouldn't actually have final simulation on this small DUT model. So here, as promised, I have simulated this on the V-bus, and I will now hide the components that are not relevant for this case to show you how this basically what we can observe. So if you remember from the contact discharge, I have this very simplified model where this backplate is now grounded through 1 ohm resistor. And here I'm having this kind of dummy display impedance, which basically means that we will have some connector that will go to the display. And I have a very, very simplified layout with only some vias. So the conductivity is not so refined. And I will just hide the dielectrics and the substrate. So here, of course, I have conducted the cause simulation, and I have put that my arc length is 0.5. We can see the voltage and also the current rise. So we can see that the current, I put a delay of 1 second, but the current goes very fast, and it goes higher than the contact discharge case. Now, how that will affect the device, I can see from the 3D, from the results of my cause simulation. And one of the maybe most important information is the surface current. So we need to place some monitor so it would be visible for us. And here I have visualized the surface current. This is the maximum, but we can also visualize the instantaneous value and maybe use some smart scaling. So we can see that at 2 nanoseconds, let's put some 1000 amperes. At 2 nanoseconds, we can see, we can also animate it, of course, but we can see how it spreads and how it dissipates in time. So if I take 3 nanoseconds, it already dissipated quite a lot. For the worst case scenario, I always like to observe the maximum value, which means that is the maximum value everywhere during these 10 nanoseconds. And based on this, well, we can make some design choices. I can tell you a few things that I would do and that I wouldn't do to refine this design. So first, I wouldn't put any sensitive components in the vicinity of this V-bus, but also we could perform similar simulation on these 2 data pins. So definitely no sensitive components in the vicinity. I would also leave as much as possible ground so that this discharge would dissipate more easily. And of course, when you build a layout, you want to divert the discharge current from any sensitive components. From here, we can see that quite a lot of discharge current will also go to this dummy flex, which perhaps would mean that the smarter location for the flex connector would be maybe somewhere on the other side where this effect of discharge would not be so great. Also, I wouldn't put this first battery contact to be the power, so to 3.8. I would rather leave this to be ground, and the other one I would assign to be of that higher voltage. But anyway, as I said, so many people can make their own conclusions. Maybe probably more of them can be made, but the main point is to have this kind of iterative approach where we can improve the design and simulate with every iteration for the best outcomes. And now we are so close to the end, so before we go to questions, hopefully you have, to give some final thoughts. So as the air discharge is such an unpredictable challenge, it is hard to replicate in physical test. It poses quite high danger for product development because it's commonly noticed in the late stages of product development. So the best way to be proactive is to use simulation during the product development phases to optimize the overall design. And my approach to this webinar was to show you how it would look on some simplified but yet more realistic scenario, and where we can identify different coupling paths and simulate also different mechanisms using static solver. So I'm now done with my part, and if that's okay with you, we can go maybe to the questions if you have any.
Thank you so much, Vesna. It was very interesting and also informative. I really like the ESD streamline. So as you said, you can basically see the sparks. That was quite cool. I have received some questions. I have put them in my presentation so everyone can see them. We have like 2-3 minutes left. So is it okay if I take over the presentation?
Yes, of course.
So let's see, I have put them here. So the first question, I hope that you can see it, is more about the CST solvers. And it's what's the difference between static, frequency, and time domain solvers inside CST?
Yes, so static solver, well, as I mentioned, it's a low frequency solver, and it is more designed to simulate this kind of electrostatic fields. So charge distribution, we can see capacitance and field strength. And in those systems, the fields are very either constant or they're slowly varying. So if we really want to have some kind of time changing fields, we would like to use then different kind of solver, like frequency or time domain solver.
Perfect. Thank you. Based on this is, I think you mentioned it briefly when you were talking about your mitigation strategies, but by simulation, how can we use components for ESD protection and specifically ESD TVS diodes? Are they enough, and how can we use them in simulations?
Yes, so of course, ESD protection, one of them are the diodes. They can be also Zener diodes, but I think nowadays are more common so-called TVS diodes. And they can be evaluated in simulation using their SPICE models. So we can apply when we have a layout. And I would, for sure, I will have in the future webinars a bit more complex model with more realistic layout. Well, I will then show how to apply the ESD diode in simulation. But in a model, we need to pay attention to different characteristics because it affects how if it will be matched to the application. For example, if the ESD, it needs to withstand itself the certain discharge level in order to be able to protect the device, because sometimes it happens that the rating of the ESD diode is lower and it can cause the diode breakdown. So what that means is that instead of having like a diode that turns on only in the case of discharge, we can have short circuit where we shouldn't have if the diode breaks, which is why we need to pay close attention to the characteristics of the ESD diodes.
Amazing. Thank you so much. And the last question is also my question. And I think you started your presentation with mentioning that ESD can damage electronics. If it's that dangerous for electronics, why it's not dangerous for human beings?
Yeah, well, that's a very good question because, I mean, we talk about like 5 kilovolts and it sounds like really a lot, and even like 30 amperes of current. But there is a difference in this kind of air discharge, not like lightning strike that can hurt people, but the duration of that pulse is very short. So it's only a couple of nanoseconds. And us people, we are compared to small electronics, quite big and squishy, and we have a lot of conductivity, which means that we can dissipate very quickly that discharge. On the other hand, the electronics, they are really tiny and they are sensitive, so just a few volts, not even kilovolts, can damage them.
Perfect. Thank you so much. This was very interesting. That was all the questions, and we are a bit over time. We have just one last slide, and this is to tell you about our event in Oulu on 12th of November. This is actually the biggest CST gathering of engineers in the Nordics. Last year we had 101 engineers from all around Nordics, and this year we are expecting even more. I know that a lot of you are planning to come, but for the ones who are not, who didn't know about this, basically the registration will be open by end of this week. So please, we hope that to see basically all of you in Oulu. That's from me. Vesna, you can have the last words.
Yeah, well, unless nobody has any questions, I would like to thank you for your time. And of course, if you have any questions, you are free to send me an email, call me, or contact me, and I will be more than happy to give advice and when it comes to electrostatic discharge simulations.
Thank you so much.
Thank you all. Have a great rest of the day.
Thank you. Bye-bye.
Thanks. Bye, all.